At this point, we should know how to simplify fractions, and we should also know how to simplify radicals. They're going to get mixed up here a little bit. Let me show you.
This is a pickle, George. This is a pickle.
Consider, if you would, two scientists doing a study, we'll say for the cure for cancer or something, okay?
Nerd alert!
One of them finds the correct dosage to be this value, okay? Seems reasonable. It's a radical in a fraction, okay? Whatever it comes out to. Now another one finds he says the correct dosage is this value, square root of 3 over 3. Okay, so they both think they have a different answer, and we want to compare their answer. And both answers appear to be in simplest term, because the fraction can't be reduced in either side, right? And the radicals are in lowest form, okay? Well, actually, we have another problem here, okay? Consider, if we wanted to compare their two answers without getting a decimal, what would we do? Consider one thing. If we took the first guy's answer and multiplied by the square root of 3 over the square root of 3. Now, I don't want to tell you where I got that, but hold on just a second. What would happen if I did? And first of all, why can I do it? Because the square root of 3 over the square root of 3 is 1. So I can do that anytime I want, okay? Why I did it, well, I'll show you, but I can certainly do it. And if I do it, what do I get? Well, in the top, I get square root of 3. And in the bottom, I get square root of 9. Big deal. Well, that was the first scientist's result. And if I compare the two, the tops are the same, and actually, the bottoms are the same too.
Fascinating.
So their answers, even though originally they looked completely different, their answers were the same, and we didn't know it. That's going to present a problem. Even though both answers were really the same, our problem was
Something wrong with us. Something very, very wrong with
the
us.
two scientists wrote their answers differently.
Oakley-dokley-doo.
The first guy put his radical in the denominator,
Oh, yes.
and the other one put his radical in the numerator. But we still want to be able to compare our answers, one with each other. We need to pick one way that we're all going to do it. We call that a convention. So, the convention is, from now on,
Great Oz has spoken.
all radicals will be in numerators only, so that we can compare things, okay?
So let it be written. So let it be done.
No radicals are allowed in denominators. So you're going to have to simplify any answer or do whatever it takes so that you do not have a radical in a denominator. This process is called rationalizing a denominator, getting the radicals out of a denominator. Now, how do we do it?
Pay attention, boys. I'll show you how it's done.
It's not so bad. To remove a radical from a denominator, basically what we're going to do is we're going to multiply the numerator and the denominator by whatever root makes that denominator a perfect root. Then he won't be a root anymore. For instance, in this case, if I multiply top and bottom by radical 2, remember why I can do that? As long as you multiply the top and bottom by the same number, you're really only multiplying by 1, and you're allowed to do that any time. And this result will be 3 times radical 2 is just 3 radical 2. And in the denominator, radical 2 times radical 2 is radical 4, but he becomes a perfect square. And you basically have removed the radical from the denominator.
You look marvelous.
Now it looks good. Okay? Well, we're allowed to have radicals in the numerator. Okay? You just can't have them in the denominator. So that is a correctly simplified answer.
Fascinating.
Now there's a couple ways to look at the, if you would, more difficult problems. For instance, this one. Remember how I told you? Multiply the numerator and the denominator certainly by the same thing. By whatever root will make the denominator a perfect root. You don't always have to use the denominator. For instance, if I use the denominator here, remember top and bottom, of course the numerator would be a radical, and the bottom would be a big nightmare, but at least it would be 18 times 18, and the square root of that number would be 18. Okay? And you think, well, that wasn't too bad, except that
Wait a minute.
I still have some more simplification to do, because in the numerator, I've got to break it into good and evil. Square root of 9 and 2, and I get 3, and then I still have to simplify the fraction.
Go ahead. Make my day.
And I'll get a final answer of radical 2 over 6. Don't even think of canceling the 2 and the 6, because a radical doesn't cancel with a number. And that would be one way to do it, but it would be a long way.
Excuse me, Professor Brainiac.
Let me give you an easier way, and then we said it from the beginning. Let's multiply by whatever it takes to make that 18 into the next highest perfect square. Well, what's the next highest perfect square that 18 goes into is 36. So if I multiply, of course I have to do it to the top and bottom. Whatever you do to the top, you have to do to the bottom, etc. The top will give me radical 2. And the bottom will give you the perfect square, the smallest perfect square, and then take the root.
You're plumb right,
I think it's a much easier way to do it. A little bit more thinking, but a lot less more computation. Okay?
It is alive.
How about this bad boy? Notice it's a cube root. Well, remember what we told you. Multiply both the numerator and denominator by whatever root it takes to make the denominator a perfect root. That's got to be a perfect cube root. Okay? If you multiply top and bottom by the cube root of 3 over the cube root of 3,
What a maroon. What an ignoramus.
why it is legal because it's 1, I don't think that's going to help you. The top will be cube root, and the bottom will be the cube root of 9, which is not a perfect cube root. We have to make it, in this case, since a whole different ballgame, a perfect cube root. So I really think the process we told you at the beginning is the better way to go. What's the next biggest cube that you could multiply? What is it going to take to multiply to make that bottom into a perfect cube? I smell 27. What does it take to get to 27?
Well, Poindexter, what do we do now?
I'm going to have to multiply the top and bottom by whatever it takes to get that to be 27, because that is a perfect cube. It's going to be 9. The top's allowed to have a root in it, and we create a perfect root in the bottom. And then we take it.
Yes!
And that's the better process. I promise you, it'll work for all roots. Okay? Remember, our goal was to get the root out of the denominator. Now, get to work. Go do your homework.